The final frontier is in space. It's the Earth itself. We have sent people to the moon, robots to the Mars and the New Horizons space probe 3.26 billion miles from Earth to snap photos of Pluto. While just 4,000 miles beneath our feet, unfathomable heat and pressure keep the center of the Earth tantalizingly out of reach. But scientists have been able to puzzle out what's inside the Earth, including olive green crystals and a rolling sea of melted iron. By studying meteoroids, volcanic eruptions, and the seismic waves from the earthquakes, today we will discuss with you on the topic what's deep inside Earth despite never traveling there. Welcome back to Signatures Live and you are watching Signatures Science. There are four main layers to Earth: crust, mantle, outer core and inner core, along with transition zones between these layers. The world we know lies on the tectonic plates making up the Earth's crust, which varies in thickness from 3 miles to over 40. Beneath the crust lies this mantle, the layer of rock making up 84% of the Earth's volume. The rocks in the upper mantle are white hot, but if you could cool them to room temperature, they would be a speckly olive green, thanks to the mineral olivine. You might know it as the August birthstone peridot. Deeper in the mantle, heat and pressure reconfigure the atoms making up olivine into two new minerals, brickmanite and ferropericlase, which are brownish orange and yellow at room temperature. Beneath the rocky mantle, there is an outer core of churning liquid iron, surrounding an inner core of solid iron. That's about 70% the size of the moon. The center of Earth is almost as hot as the surface of the sun, about 9,800 degrees Fahrenheit, with pressure that makes the comprehensive forces at the ocean floor looks like child's play. But we haven't been to any of these places inside the Earth. We haven't seen them. We haven't sent cameras or probes to bring back samples of iron glowing like coal ampoules. So, how do we know what's there? When the tectonic plates that makes up the Earth's crust move past each other, they sometimes catch and break. This breakage, along with the waves of energy that come with it, it is called an earthquake. The seismic waves unleashed, sound waves too low for us to hear, travel far from the source and can tell scientists when and where an earthquake has occurred. Detecting seismic waves isn't new. The Chinese scientist Zhang Heng built an early seismometer nearly 2,000 years ago. But in 1889, scientists had a breakthrough in using them to understand our planet. That's when a German researcher near Berlin detected an earthquake. But there was a problem. There weren't any earthquakes nearby that day. It turns out there had been an earthquake in Japan, and its seismic waves reached Germany more than an hour after it struck. It marked a pivotal point in the modern seismology. Leakey ligands seismology to the way we use X-rays to see inside the human body. The different densities of our muscles, organs, and bone mean that the X-rays travel through them in different ways. Earthquakes send ground vibration throughout our planet and they travel across the world in different ways. Seismometers record these vibrations, which can offer a glimpse of what's below. Then we can use computer modeling to try to make images of what's inside the Earth, and those images tells us essentially how quickly seismic waves travel through different parts of the Earth. Seismologists interpret data from the earthquakes and even simulate seismic activities with air guns and explosions. And their work has shown that the Earth's interior has different layers, some of which are easier for seismic waves to travel through than others. They can even tell us the densities of these layers. Then a different branch of scientists called mineral physicists take it from there to determine what actually make up those layers. One of the most exciting but also frustrating parts about these studies is that we can't go down to that depth. There's theory that makes sense, that's consistent with experimental data, because we can try to mimic what we think the conditions are, albeit micron-sized. And since scientists haven't found a way to travel to the center of the Earth, the collaboration between these different disciplines is critical to understanding what lies beneath our feet. Without kind of working together, you can't really understand the planet.